Newton's second law of motion is sometimes called the momentum principle, because the statement of the second law is that the change in momentum of a system is equal to the magnitude of the net force applied to it multiplied by the duration of time of the interaction. During that interaction, the net force needs to be nearly constant. I'm Ben, this is Physics or Bust. Now, if we limit ourselves to non-relativistic cases, where the mass doesn't change, where the motion is in one direction, and there's only one force being applied to the object, then you can simplify things and just say that the momentum principle simplifies to saying F equals ma. But to write an expression that encompasses all interactions, we have to go back to the form that Isaac Newton used when he came up with the formula. Now with F equals ma, the way I wrote it, note that these are not vectors, they're just scalars. And when we look at here, these are written as vectors. You have the change in momentum vector over a really small change in time equals the net force. This expression of the momentum principle, dp over dt equals net force, applies to every possible scenario, whether it be a big or a small interaction, say large galaxies versus protons and neutrons. It applies to fast or slow interactions, whether you're looking at neutrinos flying through space or muons flying through space, through the atmosphere, or you're looking at a ball rolling down a hill. And for every type of interaction, be it electrical, magnetic, gravitational, strong force, weak force in the nucleus, it applies for every interaction. And many times you'll see it written like this, with delta P equals the net force times time. And that's how Newton expressed his second law, was that the change in momentum equals the net force times the duration of the interaction, the change in time. So if you're wanting to get an object moving, you can either have a force acting on it for a long period of time, or a really big force acting on it for a short period of time. And this works even if you have an example like a rocket, where it's shooting material out from the back end of it, changing its mass the entire time during the interactions. But if you're going to have a system that doesn't have its mass change, then we can change this first equation to be slightly different, where it's m dv over dt equals F net. And this dv dt is acceleration. So then we have ma equals the net force. And again, those are expressed as vectors. So as long as your mass isn't changing, which, keep in mind, in relativistic terms, your mass changes just because of how fast you're going. But if your mass isn't changing, then you can write that standard way that it's been spouted all over the internet and all over books, that the net force equals mass times acceleration. In most interactions you're going to deal with, F equals ma is a perfectly fine representation of the momentum principle. Don't forget to like and subscribe, and remember, keep asking questions. I'll see you on the next video.